Hi, my name is Anjus Soares, and today I'll be talking about our project which focuses on plowing the engineering quad using integer programming. As we know, Cornell gets a lot of snow every year. When a severe snowstorm strikes, the university's grounds department does not have enough resources to keep all of our walkways and corridors clear. We decided to use the engineering quad as the basis of our model for two main reasons. First, it has an interesting layout of 20 paths. Second, it has two main groups of people which use these corridors. First, students and faculty moving from one building to another within the quad, and transient students and faculty who are going from College Town to Central Campus. So why are these characteristics so interesting? Well, with the 20 paths, the solutions that we will be getting are going to be very complex and will require a lot of computing power, as well as fine-tuning the required parameters and constraints of our functions that are subject this model to. Furthermore, because of the range of users that we are using, our model will have to satisfy the needs of two very distinct groups of people. We have only found one related work. Kinnable et al. Published a paper titled Optimization Models for a Real-World Snow Plow Routing Problem. In this, they used MIP as well as constraint programming to try to achieve a turn-by-turn solution for their snowplows. In their sophisticated methodology, they included the availability of salt and fuel, as well as the location of these salt and fuel deposits, as well as the difference between each snowplows. Our model is a lot more simplified and also focuses on the time required to plow rather than the availability of fuel. With our model, we modeled the engineering quad as an undirected 20-path system. Each corridor was broken down into segments and labeled with numbers 1 through 20. For data collection, we spent 20 minutes counting people walking throughout the engineering quad on a sunny Ithaca spring day. At our left, we see the data that we collected. Furthermore, with our model, we had to make some assumptions. We had two interchangeable and equivalent plows, maximum on the engineering quad at any single time. The time of plowing any path is constant regardless of the length of said path. Also, the snowplows would not have any start positions. Our equation model is listed below. This equation takes into account the weight of each path as well as the position of our plows. Our constraints are also listed below. Our first constraint models how we can only have one plow at most on any single path at any single time. Our second equation says that each of our plows can only be on one path at any given time. In order to get our results, we used AMPL to make our model and then CPLEX version 12.8.0.0 as our solver. Our results showed very unsurprisingly that paths 13 and 14 should be the paths that are always clear. However, we consider this a slight failure because it only suggests the two paths and nothing else. Even though we considered our model a slight failure, it is not entirely useless. From this model, we learned that the solver did give us an optimal solution for our given inputs. So we know that from now on, we need to start giving it more meticulous objective functions as well as constraints and parameters. Some possible improvements could be that the plows have to start at the edge of the engineering quad rather than anywhere on the engineering quad. Also, we could have longer observation times to have better detail. We could have observations during winter rather than spring and during class times to better model our population. Furthermore, we could have more complex conditions such as time sensitivity and to make our optimization even better.